So we're going to talk about what are called the p-series. For what values of p is this series convergent? So we have 1 over n to the p. Let's consider some different values. If p is less than 0, well, if p is less than 0, we could think of this as having negative. We could move it up, but remember p is less than 0, so this would be n to the negative number less than 0, so this would be a positive exponent. So if we have this positive fixed exponent, but we are taking 1, then 2, then 3, then 4 here and summing them up, we can see that this would go to infinity. So if p is less than 0, this limit is infinity, and this would be a divergent series. What if p equaled 0? Well, if p equaled 0, we'd have something to the 0, which is 1, so we'd have 1 over 1, which is 1. We'd be summing up 1 plus 1 plus 1, which would go to infinity, so it would also diverge. What if p was greater than 0? Now, if it was greater than 0, there's cases where if it's a fraction versus an integer or something greater, so we're going to need to look at different cases. So first we'll consider a fraction between 0 and 1. So if p is between 0 and 1, as we look at this, since x of negative p, or 1 over x to the p, is continuous, positive, and decreasing for x greater than or equal to 1, and the terms of the series equal the integer values of the function, we could use the integral test. So if we use the integral test, we would integrate from 1 to infinity 1 over x to the p dx, and so we could express that as x to the negative p. And so when we do the antiderivative, we would need one higher power here, and then we would need the reciprocal of the power. So here it is with it already being evaluated. So we are evaluating from 1 to n. So here we have this with n, and here we have it with 1. Then we take the limit as n goes to infinity, and remember that p is between 0 and 1 is positive. And so as we look at this, even though it's less than 1 because it's positive, as we take this and we go to infinity, we are going to approach infinity. So this one by the integral test diverges. Now if we looked at p greater than 1, we still can use the integral test because it's this very same thing, but now as we look at this, this is going to go to 0 because when we go to evaluate this, we have p greater than 1. So since p is greater than 1, as we increase this, since in the denominator, we're going to go to 0, and we will have this, which is finite. So by the integral test, this one will converge. Then what if p equaled 1? If p equaled 1, we would be looking at this series of 1 over n to the 1. Well, that's just the harmonic series, and we actually now can prove that the harmonic series diverges because we could use the integral test on this as well. And if we did that, as we integrate, we get the natural log of n because we had this 1 over x. If we evaluate that, we would have the natural log of n minus the natural log of 1, which is 0. If we let n go to infinity, then we go to infinity. So when it equals 1, it is a harmonic series, and by the integral test, it diverges. So looking at this, for what values of p is the series convergent? This is called a p-series, and it is only convergent when p is greater than 1. This is going to be useful to us because we are going to be looking for convergence of various series, and p-series is an easy one to know if it converges or diverges, and we'll be able to use it to kind of compare to other series that are more complex. So this series is called the p-series, and it is convergent if p is greater than 1, and it is divergent otherwise.